hello everyone, my name is Wenting. I'm a PhD student in the RISE lab, and I'm going to talk about Cerebro, which is a platform for cryptographic coopetitive learning. And this is joint work with Ryan, Weikeng, Raluca, Panda, and Yang from UC Berkeley and NYU. Okay, so let me start with the kind of the familiar use case that Raluca also mentioned earlier, which is fraud detection. So here we have a bank who wants to detect fraud using machine learning. However, fraud is a little bit difficult to detect, right, by a single bank because criminals try to conceal their illegal activities. Went too far. Yeah, try to conceal their illegal activities across many banks. So in order to compute a good and accurate model for fraud detection, ideally we want to allow the multiple banks to come together and jointly compute a model for fraud detection. However, this currently cannot happen because these banks are competing with each other and they cannot share plain text data. And there are actually many applications that can be enabled by data sharing, but simply cannot happen today because the data in question is sensitive, so we have fraud detection here. For example, you have multiple hospitals that might want to collaborate together to predict flu outbreaks across California. We actually talked to a student at Berkeley about nuclear facility auditing, which can also, you can also benefit from collaborative computation there. And also, Ruka mentioned earlier, cloud-based video analysis. So these use cases are great and can benefit from collaborative computation, but currently cannot happen because people are unwilling or unable to share their plain text data. So the question we want to ask is, can we actually allow the organizations to share their data for collaboration, but without showing the plain text data? So that's kind of the ideal scenario, right? You can still compute something, but then you don't show your sensitive data to the other parties. So you can do this with a Strawman, right? Using a trusted third party such that you send the data over to the trusted third party, and the trusted third party computes a model and then distributes the model back to the banks in this case. This is a little bit less than ideal, right? Because using trusted third party can be expensive. How trustworthy really is a trusted third party? And also, even if you trust this third party, we found that even the entity that acts as a trusted third party also is afraid of liability in case of a data breach. So the good thing is that this kind of a setting of a collaborative or a competitive learning setting corresponds exactly to a very well-known research direction in cryptography called secure multiparty computation, or MPC. And the key insight here is to allow the parties to emulate a trusted third party via cryptography, but without using a trusted third party. And the guarantee here is that no party should learn any party's input beyond what is learned from the final result. So you still want to release the final result to the party so that they can take advantage of the model. So MPC sounds pretty nice, right? It satisfies our criteria. So our banks now want to kind of use it in the real world setting. However, there are two obstacles here, right? So if you think about it, the first obstacle is kind of the generality versus performance trade-off. And the second obstacle is pretty interesting. It's about the incentives and constraints of these banks. I'm going to explain what they are. So in terms of generality versus performance trade-off, we're really looking at the prior work in this area. So really, in terms of the directions explored in the prior work, there are two main directions. One is a kind of hand-tuned MPC for specific learning tasks. As you heard from Raluca, for example, we have a project called Helen that allows you to train linear models very fast. So it's very nice to have these hand-tuned MPC systems because it offers you very good performance, but it's not quite generalizable, right? Because if you want to change it to a different model, then suddenly you have to maybe find a different hand-tuned MPC framework. On the other hand, another popular direction in this area is to kind of have a generic MPC or MPC compiler that is able to generalize to basically all functionalities, but it's often difficult for these prior works to optimize and for the machine learning setting. And they often also do not support multiple frameworks, multiple threat models, and sometimes they only support 2 parties instead of kind of arbitrary number of parties. And the second obstacle, which I find very interesting, is kind of the incentives and constraints of these parties who want to do coopetitive computation together. So let's say that these banks, right, they want to train a fraud detection model together, and our bank here at the top inputs its honest data into the computation. But what if a party actually ingests garbage data, right? Because we still have to allow the parties to be able to choose their own data. Then if they were to inject garbage data into the computation, then that might mess up the computation. Even more kind of tricky is what if a party actually injects malicious data that makes other parties misclassify in the final model. And it's called data poisoning, and I'll explain a little bit later what that, in more detail what that means. So these are very tricky if the parties actually inject bad data. But even if the parties inject honest data, they're still a little bit concerned because what if there's unintended leakage in the model that they receive, right? What if the model embeds too much information about the training data? So really, the problem here is that while, kind of intuitively, right, while MPC gives you very good privacy guarantees, it has drawbacks because there is a lack of transparency and control when it's used for this collaborative learning. By definition, if you have more privacy, then you kind of lose some control over the computation. And in Cerebro, we are really trying to tackle the 2 obstacles that I mentioned before. And in order to address these 2 obstacles, so from the generality versus performance tussle side, we actually developed a domain-specific language along with a generic MPC compiler that allows you to kind of apply machine learning optimizations to your program. And from the incentives and constraints side, we developed 2 things. So one is compute policies that allow you to kind of program policies within the original computation so that you can address these economics incentives, constraints, privacy constraints of these parties. And also something called cryptographic auditing that allows you to audit the original input that the parties input into the computation after the secure computation is complete, and explain what each of these means. But first, let's take a look at the threat model that we support. So in terms of the threat model, kind of our cryptographic backend that we're able to support, we allow an attacker to compromise P-1 out of the P parties that are participating in the computation. In terms of the attacker's power, right? So the attacker can be what we call honest but curious, or semi-honest, which means that the attacker does not deviate from the protocol, but tries to learn from the kind of the messages that he sees from other parties. The second, we also support a much stronger threat model, which is called the malicious security, where we allow the attacker we allow the attacker to actually deviate from the protocol to learn information. So maybe the attacker can input kind of inconsistent data into the computation, compute some arbitrary piece of computation that's not what it was supposed to do, et cetera, in order to learn information, right, about the other parties. So before diving into our techniques, I'm going to describe the workflow in Cerebro. So to start out with, we have an agreement phase where the parties come together, right? The banks come together and they agree to participate in this secure computation, and they also agree on the learning tasks that they want to run, and also any kind of compute policies that they want to run during the computation. And with kind of that decision, they can program that using our DSL and our machine learning API, which will result in a program written in our framework. And as you can see, it will consist of the custom learning and compute policies in there. And our compiler in Cerebro will take the program and automatically optimize it and which will result in an optimized program, and then we can use multiple backends. We will do physical planning and choose the best backend that will give you the most performance. And once you execute the secure execution, you get a result. In this case, you can get a model, or the banks can get a fraud detection model back. And later on, we still allow them to actually audit the model, as well as the original input that was used to create the model, if something goes wrong with a third-party auditor. So that's kind of the workflow of Cerebro. So now I'm going to talk about each one of these phases, starting with our domain-specific language and our API. So in our DSL, our DSL is a Python-like DSL, which supports common machine learning data types and containers. So pretty typical integers, fixed point, arrays, and matrices. In addition, there's a security tag with every kind of piece of data that you have. It can be public, right? Then that's just a public parameter. It can be private, which means that it's a kind of an input that belongs to a single party. And it can also be secret, in which case the variable, the data should be hidden from all parties, right? It should not be revealed to any of the parties. We also provide operators on these basic types, a suite of common machine learning functions, such as linear algebra operations, as well as some nonlinear operations here as well. So now I'm going to walk through an example piece of code of how you can program decision tree prediction in our DSL. So initially, in order to program the secure computation, you need to set some parameters, such as the number of parties, the size of the fixed point representation, if you choose to use fixed point representation using params, I'll set params here. And after that, after you've kind of set the configuration of the secure computation, you can now use our API to read input. In this case, because it's a prediction use case, right? You have two parties. You read the model from Alice, and you read the input features from Bob. So Bob will use Alice's model to generate a prediction for its input, but then without Alice revealing its model to Bob, or Bob revealing its input features to Alice. Here is just a prediction logic that a decision tree prediction logic that I kind of omitted, but you can program all of that in our DSL. And our program, or our compiler will be able to execute that logic later. And finally, once the decision or the prediction is computed, you can call reveal2 to reveal the result to Bob, who gets the prediction result. Okay, so that's a pretty kind of simple example program. Okay, so now I'm going to talk about the compute policies that we have in Cerebro, which, as I mentioned before, it's used to address the incentives and constraints of these parties. So as it turns out, the compute policies, because it's kind of a piece of arbitrary code that you write and you execute during the secure execution along with the custom learning task, right? It can be programmed using the same DSL that we have. As part of compute policies, we actually have a kind of subtype of policies called release policies that are pretty interesting, that use MPC's ability to on-release a result. So what happens is that you can actually, here's the secure computation we have, right? And here is our training algorithm. What you can do is actually program a piece of release policy into the secure computation such that if the output of the release policy is false, then you actually then the entire computation will choose to not release the model. And if it's true, then you will release the model. So it's kind of a programmatic way of checking whether you want to release the final result or not. And how you can use it, I'm now going to show you some example compute policies you might want to implement in your computation. So for example, so we kind of define two main categories of compute policies. One is validation-based, which are supposed to address the economic incentives in these parties. So for example, what you can do is, again, during training, right, a party might want to make sure that its accuracy gain is not greatly dominated by other parties' accuracy gain. So that you can actually program as a compute policy using our DSL. And another example, if you remember the garbage data motivation, so you can actually use cross-validation to identify a party who contributes garbage data by looking at by doing cross-validation, looking at the accuracy of the model. In terms of privacy policies, you can program differential privacy as a policy in our framework. And another policy is, let's say that if you have a machine learning technique for evaluating the model to see if it retains too much information about its training data or not, then you can use that as a release policy to unrelease the model if the checks do not pass, so that you won't be kind of unintentionally leaking information about your training data. Okay, so after you program your custom learning tasks as well as the compute policies, you can use that entire piece of program and pass it through our compiler. So now I'm going to just quickly walk through the architecture of our MPC compiler. So taking a program queue in this case, we first apply a series of logical optimization techniques. So the first technique that we have is we actually are able to automatically split the program in such a way that we can split into Q1 and Q2, where Q1 is executed using local plain text computation, and then Q2 is executed using MPC. So we are actually able to do this without affecting the security of the original program at all. And what this does, as you can see, is that it kind of minimizes, or it kind of reduces the amount of computation that you have to perform in MPC. After that, we can further logically optimize Q2, the secure computation, by using fuse operations. So these are operators that we can identify in, or I would say common code patterns that we can identify in the program that we can fuse them together for better performance. And after the logical optimization phase comes the physical planning. So in this case, we take the optimized logical program and we generate multiple physical plans based on the kind of MPC framework that you might want to use, maybe different sub-frameworks within the different phases of MPC. And so we do things like vectorization, network layout planning, and all this planning will result in multiple physical plans, and then at the end, we choose the least costly plan and then produce that, which then we can use one of our cryptographic frameworks to execute. Okay? So after you have the program, you pass it through the compiler, we produce the execution, and you run the execution, right? So the final step is kind of what happens if for some reasons something were to go wrong during while you're using the result. So I'm going to give an example here. So the problem really is what I mentioned before, the fact that we have to allow the parties to input their own data into the computation, right? So, but then that also raises a problem because they might be incentivized to provide malicious inputs. So MPC cannot force the parties to input honest data. And while you can generate some compute policies that can maybe try to detect malicious inputs, it might not always work, right? So what our solution is to add a kind of post facto check that allows us to hold parties accountable for their inputs even after the original MPC completes and after the result is released. So as an example, I'm going to give you an attack here, which is data poisoning, targeted data poisoning. So here, how the attack works is that a party injects some samples, malicious samples, with some backdoors embedded in the samples, right? It's a backdoor that, such that once you train a model, and the model is poisoned with a backdoor, then later on, any input that has the same backdoor, when you use it on the model during inference, it will actually result in a misclassification, misprediction. So this is kind of tricky, right? Because going back to what I was saying, if you could try to use compute policies to catch this, but then if the parties don't know what the backdoor is, can be arbitrary backdoor, right? Then it's very difficult to catch it. So what we try to, the way we're trying to solve it in Cerebro is to use something called cryptographic auditing. As it turns out, using a maliciously secure MPC framework is not enough, so we actually amend it with something called a cryptographic commitment, which you can think of it as something similar to a hash, right? So it has two nice properties in that once you generate a commitment, and you can publish a commitment, it's a public commitment, on your private data, right? The commitment itself is hiding in that it shouldn't reveal information about the private data that was used to generate the commitment. And it's also binding in that the party that generated the commitment should not be able to kind of find another piece of data that matches the commitment that is published, right? So using this, what we can do is, going back to the same workflow as before, here we have the honest, two parties provide the honest data, and then the third party provides this kind of poison data in here. Each party will publish a signed commitment to its data along with so that is a public input, basically. And then during the secure computation, the MPC will compute two things. So we will first compute a check at the beginning to make sure that the commitments match the input data. And then, it will compute the model, which unfortunately in this case is a poison model, right? Then during inference, a party uses this model and it's maliciously triggered by the backdoor in some input that it uses, right? So it causes misprediction. And if the party is able to actually identify the malicious backdoor from the input that was used, right? Maybe it's keeping track of the logs of the inputs that were used during inference, then what this party can do is to actually go through this auditing phase with a third-party auditor using MPC again. In this case, what happens is that each party will do a MPC or 2PC, two-party computation with the auditor, and the inputs are the private training data from each party, so that's still not revealed to the auditor, the public commitment, and the backdoor that was found, right? And if you program the right auditing function, then the backdoor should you should be able to find the backdoor in the training data of a party without revealing the training data specifically of these parties. So in this case, you identify the party that injected the malicious backdoor. Okay, so that's kind of the end-to-end workflow of Cerebro. And next I'm going to quickly go through the evaluation. So we compare Cerebro's, so we ran our experiments on EC2, and we simulated a network environment using TC, so these are the kind of network parameters that we have. In our paper, we implemented 3 applications, linear regression, logistic regression training, and decision tree prediction, and I'll only show the one application here. In terms of the baseline that we compare to, so we compare it to kind of the incorrect choice of MPC framework without Cerebro's planning, right? So with our planning, we're able to optimize and also choose the right backend you can use to execute. But then without Cerebro, then you might be able to, or you might end up making a wrong choice, right? So we're comparing to that baseline. So in terms of this is decision tree prediction, and here we fix the number of parties to 2. And as you can see, so we have two backend here, a semi-honest SH arithmetic corresponds to semi-honest arithmetic framework, and SH Boolean corresponds to a Boolean, semi-honest Boolean cryptographic framework. And as you can see, our planner is able to pick the right decision in this case always. And we see up to a 7.5x performance difference with our planner. And so here's another interesting decision tree prediction use case where you actually have multiple parties that have kind of some sort of shared decision tree model among them, and then they want to jointly do a prediction together. So in the case of multi-party prediction, it's actually pretty interesting because as you vary so on the x-axis, you're varying the tree size, right? And you can see that actually our planner is able to, again, pick the right decision, but the decision in this case is Boolean for up to, I guess, the 9-party, up to 9 parties, and then it will choose arithmetic because there's kind of a crossover here of these for these two frameworks. And in this case, we're seeing a 5.77x performance difference. Okay, so in conclusion, Cerebro is a programmable cryptographic coopetitive learning platform. And we will, as Ruka mentioned, we'll open source here. And I'm personally very excited about the future work that we'll explore as part of Cerebro. So for example, how to automatically mix protocols with a single program. So as you saw earlier, we're kind of choosing the framework that or choosing the best MPC framework that you will use during execution, but then can we actually mix multiple of these frameworks automatically together within the same program? How can we do local computation? How can we do the local computation optimization in the malicious setting? Currently, that's mostly offered in the Semana setting for now. And another very interesting direction that I'm sort of starting right now is to look at, to explore what kind of policies that you can implement, right? So our contribution is more from the system side. We are providing a platform to program these policies, but then what are some can we have some interesting theoretical guarantees for these policies? Maybe some game theory insights there. So that'll be very interesting. And yeah, that's it for my presentation. Thank you, and yeah, I guess we'll take questions. We started study showing the different MPC frameworks, and sorry, I couldn't hear. Oh, the plain text. Oh, if you were to use a centralized party? Oh, I see. Yeah. So so that's so the question is did we compare this kind of MPC execution with almost a kind of a plain text version of the system, right? Where you were to send it to a third party and compute. I mean, I would imagine the gap is quite high there because you were able to compute on plain text basically, right? But then you have to. The threat model is also quite weak in that sense because the third party sees all the data, and I think I went through the kind of the perhaps the less ideal properties of using a trusted third party. But yeah, I imagine the performance would be quite fast if you were to use a third party. Yeah, does that answer your question? I can catch up with you later. Okay, all right, thank you.